welcome back everyone. We are very happy to have Deepanshu Kush tell us something about near-optimal subheterogeneous formula lower bounds.
All right, thanks Christian, and thank you everyone for coming. So I'm Deepanshu, I'm a grad student at the University of Toronto, and this is joint work with Shubhangi, and I'm going to tell you something about lower bounds in the algebraic world. Okay, and here's the brief outline. So I'll start out by giving some background on algebraic complexity. So enough to be able to state the main results of our work. But most of the time I want to spend on really contextualizing our results and talking about the literature at large. And then if I have time at the end, I'll talk a little bit about the proofs. All right, so what is algebraic complexity? Well, it's the subfield that is concerned with the complexity of computing polynomials, and the protagonists are multivariate polynomials, so an n-variate polynomial over a field F. The models that we're concerned with are going to be circuits, so these are directed acyclic graphs with plus and times labels, and they compute the polynomial in the natural way, so bottom-up way. At the leaves you have your variables or constants, and at the top is your output gain. So there are two parameters of concern. So first is the size, which is simply the number of nodes in the circuit, and the second is what we call the product depth. So it's just a slight variation on the notion of depth that you're familiar with in the Boolean setting. So product depth is simply the maximum number of time scales that you'll encounter from a path, in a path from the root node to a leaf. Yeah, so in this example, that's 2. Okay, so given this model, we define VP, named after the computer scientist Valiant. Valiant's P is the class of all polynomials that have poly-size circuits. So polynomial in the number of variables. Okay, and also when I say polynomials, really I'm talking about polynomial family, so it's the same distinction that you make in the Boolean setting, right? So one polynomial for every n. Okay, and so this picture is an example of a what I'm going to call a sigma pi circuit. So that's because the top layer is a plus and then followed by a layer of time scales and so on. So yeah, these are analogous to AC zero circuits, or if the depth is constant and so on. So yeah, these are going to be alternating as well in the same sense. Okay, and then similarly, you can define algebraic formulas. So these are special kinds of circuits where the underlying DAG is a tree, right? So the out degree of every node is at most 1. And here's a fact that I want you to keep in mind for this talk, which is that if the depth is constant, then we need not make a distinction between formulas and circuits, because any circuit can be simulated by a small enough formula, right? So if the depth is constant, then you get a blow-up of size s to the product depth. All right, so given these two models, there are two corresponding challenges in the subfield of algebraic complexity. So you want to be able to show superpolynomial circuit size lower bounds for an explicit polynomial. And in this talk, so when I say VNP, I just mean really any explicit polynomial. I'm not going to formally define the notion of VNP. It's not all that important. And then correspondingly, even this is a major open problem, which is to show formula lower bounds. And then just to try to relate it with the Boolean setting, the problem of proving circuit lower bounds is a precondition to proving non-uniform Boolean circuit lower bounds. So if you believe that, well, NP does not have polynomial size circuits, then you're forced to believe that VP is not equal to VNP. Assuming the generalized Riemann hypothesis, but I won't get into that.
For what field size? For any field size?
Yeah, so Okay, so as far as this talk is concerned, we'll just work with any field of characteristic 0. This particular relationship gets a little bit more technical when the characteristic is finite. Okay, so these challenges are hard, right? So what we try to do is prove superpolynomial lower bounds for restricted classes of circuits. So one very common restriction is that of constant depth, or, well, in this talk I'm going to talk about product depth, so constant product depth. And then another flavor of restriction which exists in the algebraic world is that of a syntactic restriction, right? So the one that I'm going to be talking about today is that of set multilinearity. So first of all, what is a set multilinear polynomial? So suppose your underlying variable set is partitioned into d sets, then a polynomial is said to be set multilinear with respect to this partition, x1 through xd, if every term in P, so every monomial in P, consists of exactly one variable from all of the d sets. Yeah, so that's simply a set multilinear polynomial. And notice that if this were to happen, then the degree of this polynomial is, well, obviously d. And also notice that because every term has d variables, this is automatically homogeneous. All right, so correspondingly, we can define these restricted circuits, so what I'm going to call set multilinear circuits, or formulas. So an algebraic formula or circuit is set multilinear with respect to a given partition if every internal node in the formula or circuit computes a set multilinear polynomial. Right, now obviously, an internal node in a circuit need not be set multilinear with respect to the entire partition, x1 through xt, because internal nodes may compute smaller polynomials. Right, but all I demand is every internal node be set multilinear with respect to a subset of the original partition. Now, I'll make this clear with the help of an example. So this is a canonical example, the so-called product of inner products polynomial. So say you have d sets consisting of n variables each. You define this polynomial, which is the inner product of the first two times the second two, and so on. So this obviously has degree d. And you very quickly notice that when you expand this out, every term has exactly one variable from each xi. So this is a clear example of a set multilinear polynomial. And notice that if you draw this circuit out, so it's like a times gate at the top, and then followed by a layer of plus gates, and then times gates underneath. So if you look at those internal times gates, they are only set multilinear with respect to two of the sets. Right? So if you look at the node which computes the product of x11 and x21, that node just computes this monomial x11 times x21, which is set multilinear only with respect to capital X1, x2. Right? So in particular, a subset of the original partition. Okay, so that's a set multilinear circuit. All right, so that's the model of concern today. All right, here's another example, so which is that of iterated matrix multiplication, where you have D matrices, each consisting of n squared many distinct variables. And you look at the 1/1th entry of the product matrix. So that, of course, is a polynomial. It's a set multilinear polynomial. And that is what I'm going to call IMM n comma d. Yeah, so d is the degree of that polynomial. All right. Notice that if you just consider one matrix, the determinant as well as the permanent, when thought of as polynomials, are set multilinear with respect to, say, the column variables or the row variables, right? Because every term in the permanent polynomial consists of exactly one guy from each row or each column. So just keep that in mind. Then with the definition of IMM, I'm now ready to define this other class, which we call VBP. So this is the class of polynomials obtained by replacing the variables in the IMM polynomial by linear forms or constants. Right? So this big polynomial that you get in terms of whatever xi comma j, you just replace all of those xi comma j by variables of your choice, so say some y variables, or linear forms in y variables, or by constants like 0, 5, whatever. So all sorts of polynomials that you can compute by doing this process, that class is what I'm going to call VBP. Right? And this can be very quickly seen to be an algebraic analog of a branching program. So that's why this class is called, well, basically variance branching programs, let's say. So therefore, it can also be seen as the algebraic analog of the class NL/poly. Right? And the way that I've defined it, you can also see that IMM is a complete polynomial for this class. So completeness, I'm not going to define it formally, but it just means that you can restrict IMM to get your polynomial in this class. Okay, so that was the background. Now I'm ready to state our results. So here's the main result. So say delta is a constant. It's like 5 or 2 or 3, something small. We show that there's an explicit set multilinear polynomial over n squared many variables with degree that's equal to n, such that any set multilinear formula of product depth delta computing our polynomial must have size that's this expression, n to the d to the 1 over delta. So in particular, if delta equals 2, this is n to the square root d. So that's the first result. And the second one is if there's no bound on the depth, then we show this bound, so n to the log n, for any set multilinear formula computing our polynomial. Yeah? Okay. So now let me talk about what this explicit set multilinear polynomial is. So in prior work, we constructed this polynomial. It's some explicit polynomial, and it happens to sit in this class VNP that I told you I'm not going to define. And in the new work, we've managed to construct polynomials that are now computationally simpler. So they now sit inside set multilinear VP. And we've also managed to construct a polynomial that's in VBP. So in particular, it's a restriction of IMM, right? And for which we have these very strong lower bounds against. Okay, so that's just the main result. Now the rest of the talk, I really want to basically contextualize these results. So if these expressions seem mysterious now, hopefully by the end of the talk I can convey why these bounds are interesting and why these bounds in particular. Yeah? Okay, and before I get to that, just one quick thing. By known results in the literature, these bounds that we obtain are essentially optimal. All right, so let's talk about the context. Here's the starting point, which is a very recent breakthrough, for which the setting is as follows. So although, as you all know, constant depth circuit lower bounds were known in the Boolean worlds since the 80s, they actually remained elusive in the algebraic world for a very long time. And obviously, if you want to solve the grand challenges in algebraic complexity that I mentioned earlier on in the talk, you have to be able to show strong lower bounds against constant depth, right? So they're a necessary precursor to the grand challenges. And only a couple of years ago, they were shown for fields with characteristic 0 in a two-step process. This is the work of Limai Srinivasan and Sebastian, who's here. Okay, and in fact, they were shown for the IMM polynomial itself, so our canonical example in VBP. Okay, but before I get to this two-step process, let me just mention something about IMM upper bounds, or IMM algorithms. So IMM happens to have, so IMM n comma d, it has a very simple divide and conquer based set multilinear formula of size n to the order log d. Yeah, if you've seen the proof of Savage's theorem, or like it's just the same idea, divide and conquer idea. And then if you want to force your formula to have constant depth, then you can construct it using this size. And these formulas are indeed set multilinear, but even if you do not impose the set multilinearity constraint, no significantly better upper bound is known. So therefore, it seems reasonable to conjecture that these bounds for the IMM polynomial are tight, up to the constant in the big O. Yeah, so Okay, so now going back to LST, what they do, so they want to show constant depth lower bounds, sorry, super polynomial sized lower bounds against all constant depth circuits, right? So what they do is, so you start with a product depth delta formula, and the first step is to set multilinearize it. So you blow up the depth a tiny bit, so a product depth delta becomes product depth 2 delta. You incur this particular size blow up, but the resulting formula is now guaranteed to be set multilinear. That's the first step. In the second step, they establish lower bounds against set multilinear formulas, computing IMM, which the quantitative expression is this. That's not super important for now. But the thing to note is that this entire framework works when the degree is small. I know that that's necessary, right? Because if you start with a poly-sized formula, because of this big blow-up that you have here in terms of D, you need the resulting formula to be poly-sized as well. And therefore, the degree has to be small, right? So this small degree condition is necessary. And also want to comment that this set multilinearization of general formulas with a similar size blow-up was already known. This is a work due to Ross. But the problem was this work, it did not preserve the depth. And so the main contribution of LST here is to make sure that you can do this process while maintaining the depth of the formula. Okay, so now a word on Ross's set multilinearization. So what Ross does is, starting from a general formula, he obtains a set multilinear formula with this size blow-up. The point is the following. If you start with a set multilinear polynomial of small enough degree, so degree at most log n divided by log n, then it has a general formula of size that's polynomial in n, if and only if it has a set multilinear formula of poly-size. So stated in the contrapositive, this means that if you're able to show super polynomial lower bounds in the set multilinear setting, when the degree is small, that would imply super polynomial lower bounds for general formulas, right? And thereby resolving one of the grand challenges. So it's clear that the two results that I mentioned, Ross and LST, that studying set multilinear complexity when the degree is small can be very, very consequential to our field. But I want to try to convince you that even the large degree regime can be equally consequential, right? So to this end, in a follow-up work, LST, they showed the first super polynomial lower bounds against unbounded depth set multilinear formulas, computing IMM n, n. So that is when the degree is large, when the degree is n. Okay, and I'll talk about this in a second. But okay, so here we go. Why is the large degree regime consequential? And it's all down to this self-reducibility property of the IMM polynomial. So it turns out that it is possible to construct formulas for IMM n, n, so the large degree setting, using formulas for IMM n, d, where d is smaller than n. Right, so what this means is that if you had formulas of size n to the little o of log d for the smaller IMM, then by using a combination of those formulas, you will be able to get a smaller formula for your original IMM. Right, and again, stating the contrapositive, what this means is that if you're able to show an n to the omega n lower bound in the large degree setting, then that implies some super polynomial lower bound in the low degree setting. But hey, once you're in the low degree setting, you can now use the framework of Ross that I mentioned on the previous slide. So this would imply super polynomial lower bounds for general formulas. So overall, proving the optimal n to the omega log n set multilinear formula size lower bounds would have dramatic consequences. And okay, so if you didn't follow every single step in this previous slide, the only thing to keep in mind is this upshot. So using folklore results in our field, essentially this is what it boils down to. So if you want to show general algebraic formula lower bounds, so which can be thought of as showing NC1 not equal to NL in the algebraic world, if you want to do this, then it suffices to show the optimal n to the omega n lower bounds, set multilinear formula lower bounds for the IMM polynomial. That's the upshot. So what is the progress that's been made towards this end? So in a follow-up work, LST, they're able to show a weaker bound where the base of the exponent is log n. So you may think all we have to do is simply improve the base from log n to n. But unfortunately, it seems we're far from achieving it. And we don't even have the optimal lower bound when the depth is constant, when the depth is 2, right? And it's not that we don't have this for the IMM. In fact, we don't have this for any explicit polynomial when the degree is large, when the degree is n. Right, so the best that we have is, again, due to the same follow-up of LST, which is log n to the omega square root n, which improves on prior results due to Nissan and Victorson. And for constant product depth, this is the result that they're able to get. So prior to our work, the question that we asked ourselves is, can we at least improve this base from log n to n for some explicit polynomial? Hey, maybe we won't be able to do IMM just yet, but can we do it for some explicit polynomial? Yeah, so now stating our results again, well, we do manage to accomplish this for some polynomials. And so in prior work, as I mentioned, we do this for some polynomial in VNP, so some explicit but computationally hard polynomial, or we believe to be hard polynomial, VNP. And then in this new work, we've managed to simplify the polynomial from something in VNP to first something in VP, and then something even in VBP. Right? Okay. So yeah, as I mentioned earlier, why are these results optimal? So let me just quickly talk about this paradigm of results in the algebraic world, which are called depth reduction results. Actually, the analog of which do not exist in the Boolean world. So this is something very special about the algebraic world, which is that, say you start with a general formula, computing a polynomial, and I ask you the question, okay, what is the size blow up that you need in order to squash this formula, general formula, down to a constant product depth, to a product depth 2 or 3, right? What is the blow up that is needed? And so Sebastian, building on some prior works, has a result which shows that any circuit of poly-sized, computing an n-way degree D polynomial, can be set multilinearized. Sorry, it can be squashed down to a product depth delta set multilinear polynomial of this size. Right, so notice that this is the exact same expression that we have in our lower bounds. So what this means is that our lower bounds are super strong, and in fact they're sharp. So they're sharp in the sense that, yeah, so if the polynomial is in VP, so if it already has small circuits, it means our lower bounds are optimal. But if the hard polynomial is in VNP, it means that any asymptotic improvement in our results would imply super polynomial lower bounds for set multilinear circuits. Right? So we get circuit lower bounds in some restricted setting if we're able to improve these lower bounds, even a tiny bit. Yeah, and so far in the algebraic world, the only restrictions for which we know circuit lower bounds are, of course, constant depth, again due to work of LST, and the monotone setting, which I'm not going to talk about. But all right, so finally, what are these explicit polynomials in our work? Right, so in our first result, it's a popular polynomial in VNP. It's built from these Nissan-Wigderson design-based family of polynomials, which we've seen a bunch over the last few days. And okay, I'll skip this point. But yeah, and then so in our new result, the point is simply that we improved the complexity of this polynomial from something that was previously in VNP to now in VP, and also we give a construction VBP. Right, so the first one is based on this very nice combinatorial notion of Dyck words. You've seen that. If you've seen the definition of Catalan numbers, that's what that comes from. And one in VBPs. This is due to a prior result of Dwi, Malod, Perifel, and Yehuda. All right, so I have 5 minutes.
For questions.
Okay, for questions. Okay, I have half a minute. All right. So it's okay. I probably won't be able to talk about the proof overview, but that's okay. The only thing, the one point that I wanted to mention before I end is the following. So you may think to yourself, well, I mentioned two things to you, right? Which is that we are able to construct a set multilinear polynomial in VBP for which we have optimal set multilinear formula lower bounds. And I also mentioned to you that IMM is complete for this class, right? And then I also mentioned to you, if we have the lower bounds that we have for our polynomial, if we're able to show them for the IMM, then we have formula lower bounds, right? So you may think to yourself, wait, aren't we done already? Because the IMM is complete for this class, right? So aren't we done? And so, but here's the catch. Okay, so IMM is complete for this class VBP. So indeed, there's a way to obtain our polynomial from the IMM by restricting variables to constants or linear forms. And so doesn't this imply lower bounds for the IMM? Well, unfortunately, no, because this restriction, when you apply it to a formula that computes the IMM, it unfortunately destroys the set multilinearity. So the super strong set multilinear formula lower bounds that we're able to show for Pn then do not apply for IMM, right? So yeah, it doesn't work. All right, so yeah, just the final slide, which is, yeah, by far the most interesting problem now as a consequence of our work is to make the hard polynomial IMM. And so this would show NL is not NC1 in the algebraic world. And yeah, the story is, yeah, we started from the N Nissan-Wigderson polynomial, and we've made it computationally simpler from something in V and P to something in VP, and now something even in VBP, but not quite IMM just yet. And perhaps we are just one key idea away. So that's where I'd like to end. Thank you.
Thank you very much. Questions? Yes, please.
Yes.
So there's an old result by, I think, Raz and Yahudayev. They made some polynomials with two-source extractor kind of thing.
Okay.
Some discrepancy argument to show lower bounds. Do you see any connection or any relevance of that kind of construction to yours?
I'm not familiar with that work. Like, there is a work of Raz and Yahudayev that I cite, and we use. They have some lower bounds in the multilinear setting that we have to work a little hard to make sure they also apply to the set multilinear setting, but I'm not aware of this extractor stuff.
There is a generalization of two-source extractors, which is, I think, called mixed-order two-source extractors, and they take one of those and they build a polynomial out of it. This Nissan-Wigderson reminded me of that. So
I see. Okay, unfortunately, I'm not aware of it, but I'll look it up. Yeah, sounds interesting. Thank you. Yeah.
Can you explain again why the restriction from IMM to linear forms and constant doesn't breaks your idea?
Sure. So, what do we want to show? We want to show formula lower bounds for the IMM polynomial, right? So you start with a set multilinear formula computing the IMM polynomial. Right? And what we have is set multilinear formula lower bounds for our polynomial P, some P. Right? And what we know is that if you apply some sort of a nice restriction to the IMM, it gives you our polynomial P. But unfortunately, let me just quickly.
What is the restriction? It's a projection.
Yeah, a projection, yeah. So the unfortunate thing is, so let's say this is our polynomial P, which is set multilinear with respect to, let's say, these Y sets. So P can indeed be obtained from some IMM. Actually, this D and D may not be the same. So yeah, P can be obtained as a restriction of some IMM, but the problem is, the way that we construct our polynomial, linear forms that you end up needing, they end up being linear forms over not just the y1 variables, but also y2, y3, yd. So the order is not preserved, right? So once you get variables from the other sets, and once you try to multiply all of them out, the set multilinear just goes out the window. So that's one of the challenges that we're trying to work on, is how do we make sure that this order is retained? It may be easy, may be hard, I'm not sure.
Thank Deepanshu again.
Thank you. Oh.